Welcome. This is 2048 T2 from Spring 19, and what I'm going to do today is just review the questions in the key and how I approach them to give you a bit of background. So the first thing is just reminding you that there's some issues up here. There's no equation sheet allowed, so you need to know your equations, and you must show work. You can't just show the answer when it's a complicated question. If it's conceptual, it's no problem, but if there's some detailed work, you need to show it. And then if you forget units, then your score will eventually be reduced. And please use standard symbols, just so that we can all follow what you're writing. Please put one final answer in a box. Sometimes people will put two answers down, and sometimes it is a choice between two answers, and the physics is you have to determine which one it is. So if there's two answers, then there's no points. Cell phones in your bag. This is about how we conduct a test. No smart watches allowed. Actually, you can't return. I'm sorry, but if you leave a test, you cannot come back. I've had some bad situations where people have left and then come back and done wonderfully after they come back. And then we have assigned seats in the test. And no graphing calculators because they can store equations. We use scientific calculators. I'll go through that with people. The key thing with many of these things is to, first of all, recognize what kind of question it is and where you are. And there is some help in that they're usually in the later tests numbered with the chapter heading. So this is from chapter F. And so you can say, oh yeah, chapter F, I remember where I was on that. This first question says a 6 kilogram aeroplane travels straight and level, moving at a steady 32 meters per second to the right. Its engines provide a thrust of 45 newtons. Is the plane in equilibrium in the vertical axis? And so typically on this, I'll need a diagram, and I have a diagram over here. And what this diagram is telling me, well, what the words are telling me is that there's a mass, and so there's a weight. But it travels straight and level, so there must be a lift. It's traveling at a steady speed, so although there's a thrust, there's also a drag. The zero velocity upwards, because it's flying straight and level, means that it's in equilibrium upwards, and the constant velocity sideways, because it's 32 meters per second, means that it's in equilibrium horizontally. So it says, is this plane in equilibrium in the vertical axis? The fact that I'm not accelerating upwards or downwards, the fact that I have a constant velocity upwards or downwards, which in this case is 0 meters per second upwards or downwards, means that I am in equilibrium. So the answer to that one is yes. If you just think about the named forces or the obvious forces, you can get misled with this. And so it's important to have a good diagram. In this second question, I'm moving on to the next big challenge, which is basically using Newton's first and second law. In this one, we're going to do a numerical value on Newton's first law. It says a 6 kilogram traffic light. There's my 6 kilograms. Sorry, I have to get this back. Okay. There's my 6 kilograms. Hangs from two wires as shown. The right hand wire makes an angle of 30 degrees. And the left-hand wire makes an angle of 45 degrees. Oh, I jumped a bit there, didn't I? 30 degrees to the horizontal is very different from 40 degrees to the vertical. And I'm being deliberate about that. I'm deliberately not giving you them both to the same axis. I want to see what you do with that. And then find the tension in the right-hand wire by drawing a scaled vector diagram. So I want to see this structure. I'm actually giving you a vector diagram problem. And, well, where do I begin? Well, the first thing I recognize is that this object is in equilibrium in any axis I choose. It's not accelerating in any direction. And so I can start with what I know, which is that it's 60, because it's mg, it's 60 newtons pointed downwards. And then the second thing I know is that the tension in the right hand wire goes at 30 degrees to the horizontal. So I can draw that line in. I don't know where it ends, but I know the process of addition. If I add the three vectors, the weight, the right hand tension and the left hand tension together, if I add those three vectors together, they must form a closed triangle, because there's no resultant, because there's no net force, because there's no acceleration, because this thing is in equilibrium. So there's a logical flow to that. And so I don't know the size of this second vector, but I want to add it to the first vector, and the process of addition is you put the tail of the second vector on the head of the first vector. I know its direction, I just don't know how long it is, so just draw it. And then for this final step, again, I know T left must be, well, it's 40 degrees to the vertical, but I don't know where it begins, but I do know where it ends. And so I can do 40 degrees to the vertical there. So I know it ends here. I draw that line all the way back. Sorry, my pen is, I've never used the pen like this, so I'm learning. Let's try this again. So I draw the line all the way back, and what I find is wherever these two guys cross is the end of them and the beginning of them. So now I can say, well, let's measure this length for T right and convert it back in using the scale, and I find it's 39 newtons. So you pick a convenient scale. You might say 10 centimeters, 1 centimeter equals 10 newtons, and just draw it to scale. So very good skill. In this next question, a 7 kilogram bus pushes a 5 kilogram car, causing it to accelerate from 0 to 30 meters per second along a straight and level section of 275. Which statement below is correct for this period of motion? And it's asking us about the force of the bus on the car and the force of the car on the bus. And it's asking which is bigger, or are they equal? And the visualization is we have our car, we have our bus, and it's pushing our car. And it's going at it's actually accelerating. It actually doesn't matter whether it's constant speed or whatever. It doesn't matter, because the force of the bus on the car and the force of the car on the bus are an action-reaction pair, and so by definition they are equal. So the question is, where does the acceleration come from? And the acceleration comes because the force of the bus on the car and the force of the car on the bus are internal forces, and so I don't even use those to get the acceleration. I compare the force of the air resistance pushing back on the car with the force of the road pushing on the tires, and if those two are equal, I coast. If the force of the air pushing back on the car is bigger than the force of the road pushing on the tires, then I decrease my speed. And if the force of the air pushing back on the car is less than the force of the road on the tires, then I increase my speed. This next question. A 5 kilogram traffic light hangs from 2 wires as shown. So we're back with a traffic light. The right hand wire makes an angle of 30 degrees to the horizontal. The left hand wire makes an angle of 45 degrees to the horizontal, to the vertical axis. Find the tension in the right hand wire using one of the methods of trigonometry in class. So you can't do the diagram for this one and get credit. You've got to show me the trig. Again, I've chosen not to have to have the angles to one to the horizontal and one to the vertical to see what you do with your trigonometry. There's several ways of doing this. I can resolve the forces horizontally and get one equation, and resolve the forces vertically and get a second equation. That's slow, but it will get you there. Both forces are involved in the both equations. A second way, which is quicker, is that you say to yourself, I don't care about T left because I want to find T right. It says find the tensional force in the right hand wire. So I don't care about T left. So I draw my diagram carefully. The better you draw these angles, the better your diagram is. I draw my diagram carefully, and I recognize the fact that I don't care about T left. And so I choose to form an axis which is at 90 degrees to T left. T left has no component along this axis, and so it still exists, but it is not part of the equation I'm now going to write. And I can then do what I always do, which is I resolve my forces along this line. Well, there's two forces that have components along this line. T right has a component along this line, and I can construct that by making my triangle and recognizing that T right is always the hypotenuse. The original vector is always the hypotenuse, and we have an angle of 20 degrees between what I want and what I have. And I got that 20 because I recognize the fact that if this was 50, if that's 50, that's 40 to make 90, and we were told originally that's 30, so 40 and 30 make 70, which means this middle angle here is 20. Okay, so I can say T right cosine 20 for my component, and then I look at my second vector, the 50 Newton vector, and again using geometry I can see that the angle between the vector component along the axis and the weight is 40 degrees, and again I'm using a hypotenuse and an adjacent, so I can say this is 50 cosine 40. One of these must be positive and one of these must be negative. Let's make that the positive end, let's make this the negative end, and I can say, okay, the sum of the forces along the red line, it was originally red, is equal to 0. So TR cosine 20, which is in the positive direction, added to minus 50 cosine 40 in the negative direction equals 0. Rearrange, substitute in, and I get the answer. The trick with this problem is you have to be able to decide where to put the axis so that you can ignore the unknown force that you do not want. I can't emphasize enough, a big, well-drawn diagram is essential in this question. So really get a protractor and just learn to draw your diagrams carefully. The fact that this angle looks like 20 versus this angle which looks like 30 is just really helpful. It makes this whole project much easier. And then we have the next question. So now we're changing chapters. Now we're going on to chapter G, which is all about dynamics, statics and dynamics. So we say a 4 kilogram block rests on a rough table. So no diagram here. Well, there's a little diagram at the side, which I need to make my own. So I do it here. So I have a 4 kilogram block resting on a smooth table. Oh, a rough table, I'm sorry, rough table. That means the friction. There is a 0.5 coefficient of kinetic friction between the block and the table. a 9 kilogram load is connected to the block by a string that passes over a massless, frictionless pulley. What is the tension in the string once the system is free to move? The problem with this is that a downwards motion on this object would be regarded as negative if I use my normal process of assigning signs, whereas the motion that causes it on this axis is a positive motion. So a positive motion inevitably becomes a negative motion, and all my signs get confused. So the way to solve this is you just unwind, you stretch this out in a straight line. So again, yes, I have my weight. 90 newtons is my weight. I can put my weight in. And I have my mass, and then what's holding that mass back is of course tension. So I have my tension, and then that tension is in an action-reaction pair with this other tension, which is pulling the 4 kilogram mass forwards. But the 4 kilogram mass is held back by a force of friction. And so I turn around and say, I need to find my force of friction. So I say, well, FF is equal to mu k times Fn, and I know my mu k is 20, and I can see, can I? If that's 40 in terms of weight, then Fn is in equilibrium with it, and so that will be 40 newtons as well. So I get FF is equal to 0.5 times 40, which gives me 20 newtons. So I've just worked out the value of FF. I can put it into my diagram. Okay, so let's try and solve this. We can pick either the 4 kilogram mass and look at the external forces on it, or we can pick out the 9 kilogram mass and look at the external forces on that. I'm here today, I'm choosing the 9 kilogram mass. There's no particular advantage. I just picked one. And I say, well, the sum of the forces on the 9 is equal to the mass of the 9 times the acceleration of the 9. So this is 90. It's in a positive direction. 90 minus t. T is in a negative direction, so we add on the negative, is equal to the mass, which is 9 times the acceleration. Rearrange, t is equal to 90 minus 9a. Okay. Problem is, don't know what my acceleration is. Okay, the easiest way to do this is to, if you think about it, I've got several unknowns. I've got the tension and I've got the acceleration. So again, I want to try and find an equation that does not have tension involved. So I can simply consider the two masses and the string between them as one object. We'll call it the system. So I say the sum of the forces on the system. Now it's net external forces, and that equals the mass of the system times the acceleration of the system. And the net external forces on the system are plus 90 at one end and minus 20 at the other. And they equal the mass of the system. Well, the mass of the system is both these original masses, so 9 plus 4 times A. I like to write the 9 plus 4 down to tell myself that I did add the two of them together when I check my work. Rather than just saying 11, rather than just saying 13, I'm going to put down 9 plus 4. So I'm doing math. I say 9 plus minus 20 is 70, and 9 plus 4 is 13. So I get 70 over, I can't see it because there's a little thing in front of it. So my A equals 5.3 something. I substitute in, I do my math. So can you see how the math is actually the last step? It's what math you do is the right step. Let's look at the next question. A recall question. I like to get recall in because sometimes I worry that people don't look at the notes beyond what they need to look at them for. The notes are basically my designation of what's essential. I really do want you to know what's in the notes. If it's in the notes, unless I say don't worry about it, it really is essential. So recalling the notes, carefully draw the trace of this diagram. And what we realize is, of course, the frictional force versus the applied force. And what we realized is that the static friction, well, when you have a small applied force, you get a small frictional force, a bigger applied force, a bigger frictional force, and so on. That increases linearly. And then for the kinetic friction, what happens is that you have a pretty constant value, and it dips down from the maximum value. Yeah, it dips down from the maximum value. So that's what I was looking for. So just recall on that one. I could show you the trace and actually ask you what the axes are and things like that. Next question. Which trace best represents the relationship between the frictional force and the normal force for an object that is moving? So I got a frictional force and I got a normal force, so hopefully that's, I'm in a frictional world. Find an equation that links them. FF is equal to mu k times Fn. And then I'm saying, well, is this inverse? Is it inverse square? Is it a quadratic equation? What is it? Is it linear? What is it? And I look at this, and the thing to do is to look at your axes. There's FF. Well, my y-axis is FF, and there's Fn, and my x-axis is Fn. So this is a linear relationship. Y equals slope x plus b. So I recognize it as linear. There's two linears on this choice. There's a linear where if you increase x, you get more y. And then there's a linear where when you increase x, you get less y. And clearly, if I increase my Fn, I get more FF. And so there's my choice. Okay, cool. So the answer is D. Next question. A 6 kilogram block accelerates down a slope. The friction force between the block and the slope is 4 newtons. The slope is inclined at 35 degrees above the horizontal. What is the acceleration of the block along the slope? Again, I have to begin with a good diagram. Frankly, on tests, I don't make much effort to give you a good diagram. I want to see if you can draw a diagram, so the diagrams that I draw tend to be schematic rather than anything else. So I draw my slope, and small object, big arrows, and I know that the weight is 60 newtons, so I can draw that. It's vertically downwards, and I know I have a normal force, and I know I have a frictional force. I know the angle is 35, so I get myself set up with a good diagram. What is the acceleration of the block along the slope? So let's put our acceleration in. Our acceleration is along the slope. It's going to be down the slope, and it's going to be caused by the resultant of these two forces, the Fn and the 60. I say, well, the sum of the forces along the slope. When you have an acceleration, always resolve your forces in the line of the acceleration and see if you can solve in one step. If you cannot, then you can resolve your forces perpendicular to the acceleration, and you can say the sum of the forces perpendicular to the acceleration equals 0. So in this case, I'm in line with the acceleration, so the sum of the forces along the slope is equal to ma. And I'm looking at my diagram, and I know that, I have a 4 Newton force upwards. I have a component of my weight down the slope. And what is that component? If this angle in the corner here is 35, I know this angle at the bottom here is 35. I can actually see it's the smaller angle. And I know that I have the hypotenuse and I want the component which is the opposite for this triangle. And so I say this is 60 sine 35. So I have plus 4 and I have minus 60 sine 35 because it's in a negative direction. And that equals my mass, which is 6 times my acceleration. And so I say, oh, this is just math. It comes out to be minus 30.414 equals 6a. So a is equal to minus 30.414 over 6, which is that. Sometimes, so let's point this out. This is telling me I have a negative acceleration. And the reason why I get the negative sign there is because I didn't put the negative sign on the letter A. Some people will recognize this is a negative A, just as they recognize that's a positive 4. Just as they recognize that's a negative 6 sine 35. So I could have written 4 plus minus 60 sine 35 equals 6 times minus a. If I'd have recognized that it was a negative acceleration in my original equation, I would have got a positive acceleration in my answer, meaning, oh, you add the negative sign there, this is the size of it, because you've already put the negative sign in. So sometimes people miss the negative sign out on the A and they get a negative numerical value. Or sometimes put the negative sign into the A, in which case they get a positive numerical value. But when you take both of those together, it's the same answer. Just watch out for that. Circular motion. A block moves in a circle. It has a centripetal acceleration of 4 meters per second squared. What is the centripetal acceleration of the new block if it has twice the mass, 4 times the velocity of the old mass, and it follows the path that has half times the radius of the old path? So I do 2 diagrams. There's my one diagram, that's the old version, and here's my new version. It's a classic ratio problem. And I say, well, the new centripetal acceleration over the old centripetal acceleration is the new centripetal acceleration over the value of the old centripetal acceleration, which was 4. Now I know centripetal acceleration equals v squared over r, so the new centripetal acceleration will be the new v squared over the new r, and the old centripetal acceleration will be the old v squared over the old r. Well, I don't know the absolute value of any of those, but if I look here, I can see it has 4 times the velocity of the old mass. So let's just say the old mass was equal to 1 and square it. Well, the new one is 4 and square it. And it follows a path that has half the radius. Well, let's say the old value was 1 and the new value is a half. Can you see how by doing it that way it makes it very simple and all the old stuff just becomes 1? So I get 4 fours is 16 over half is 32. So my new centripetal acceleration over 4 is equal to 32. So my new centripetal acceleration is equal to 32 times 4, which is 128. And I have to be honest with you, there's a lot of times when students will give me the answer of 32 because they end there, because they're doing it in their head, because they're not writing down this algebra at the beginning, which is a mistake. We want you to write in equations. That's what part of the training is. Difference between an experienced engineer and a novice is the experienced engineer writes in equations. So we want you to write in equations, And we're setting up problems where, frankly, if you don't write in equations, you may well make a mistake. So be sure to write all of this down. I'm not teaching you, I'm showing you what I do to get these problems right. So go with it. Next question. 4-kilogram model car drives as fast as it can around a level unbanked circular track of 12-meter radius. There is a 0.6 coefficient of friction between the car tires and the track. What is the maximum speed that the car can travel at without slipping? Again, I need a good diagram. I didn't draw the full circle in, but there's the middle of the circle. Let's see if we can do that. There's the middle of the circle, and here's the car. And well, let's have a look. It's on a level track. Well, the car's got a weight, so there must be a normal force. And of course, there has to be a centripetal acceleration, which I didn't draw in actually, but it's in that direction. And that is paid for by a force. And the force in this case that pays for that centripetal acceleration is the frictional force. And the radius is 12 meters, and there's a velocity. I kind of draw it as a curvy velocity. It's actually coming out of the page towards us, but I drew it as a curvy velocity. It's a very standard setup. There's 4 classic setups for this part. And I know that the sum of the forces horizontally, that's where the acceleration is. So the sum of the forces horizontally equals mass times acceleration. It's just like the previous chapter. Find the acceleration, sum of the forces equals ma in that direction. Try to solve in one step. If you can't solve in one step, go 90 degrees and see what you can do. So this is ma, but it's a special kind of acceleration. It's centripetal acceleration, which equals mv squared over r. And so I say, well, 24 is equal to, so then, I'm sorry. So then I say, well, ff is equal to 4 times v squared over 12. And I don't know what ff is. So I say, let's find ff. And I say, well, ff is equal to mu k times fn. ff is equal to 0.6 times 40. It tells me the 0.6. The mass gives me the 40. That gives me 24. So 24 is equal to 4 times v squared over 12. V squared is equal to 24 times 12 over 4, which equals 72. V squared is equal to 8.5 about. But it's, even though it's in circular motion, it harks back to Newton's second law. Yeah, let's look. Now we have non-uniform circular motion. This is circular motion where you're not going at a constant speed. So there's going to be centripetal acceleration. Anytime you go in a circle, you have centripetal acceleration. But there's also going to be tangential acceleration because you're speeding up or slowing down. Question says a particle has a tangential acceleration of 3 meters per second squared. So I give you that value. It has a centripetal acceleration of 6 meters per second. Oh, it's very kind in this case. I gave you that value. What is the net acceleration? So, okay, we have a tangential acceleration, which is tangential, and we have a centripetal acceleration, which is radial. And so they must be at 90 degrees to each other, and so that forms a nice rectangle. And my resultant, the net acceleration, is a sum of these guys, and that basically gives me a nice triangle to work with, and I can use Pythagoras. So I say my net acceleration is equal to the square root of tangential acceleration squared plus centripetal acceleration squared, which is the square root of 3 squared plus 6 squared, which is the square root of 45, which is that. So they don't always, I like to ask a lot of questions, so sometimes I will make you work for some of the information, and sometimes I'll give you the information. And that was a case where I gave you more of the information. Here's another non-uniform circular motion we have a 9 kilogram ball is attached to the ceiling by a rope that is 4 meters long. Well, that rope is going to provide the force that causes the centripetal acceleration. It's going to have a tension in it. 4 meters long. And the ball is swung in an arc forming a pendulum. Now that's just told me that it's non-uniform, because a pendulum stops and then goes fast at the bottom and then stops again. So the speed is changing. The speed of the ball at its lowest point is 8 meters per second. So I have that. And what is the tension in the rope at its lowest point? So I want to find that tension. My diagram is not complete. I don't even mention the weight, but of course there's 90 newtons pointing downwards. And so I say, I want to find the tension at this point. I need to resolve my forces vertically, because that's the line that the tension is on. My acceleration at this point is vertical. So I say the sum of the forces vertical equals the mass times the acceleration vertically. But this is a special acceleration, it's centripetal acceleration, so it's m times AC, which equals m times v squared over r. Then I look at my diagram and I say plus tension added to, there's only one other force, it's negative, minus 90, is equal to 9, that's the mass, times v squared over r. And so I say my tension is equal to 90 plus 9 times 64 over 4 is 144, and we add them together like that. There's a point I'm skating over a little bit here, is that in this diagram the centripetal acceleration is pointing upwards, so that 8 squared over 4 is a positive 8 squared over 4. If I had a Ferris wheel so that the centripetal acceleration could point downwards, I'd need to take into account the fact that I had a negative pointing centripetal acceleration. But again, it's Newton's second law, isn't it? Again, it's Newton's second law. Next chapter. So now we're on energy. A force of 4 newtons points in a negative y direction, so there it is. Why not draw it if you can? And then the force is moving through a displacement of that. I have no idea where that is. I'm not going to draw it to scale. I'm just going to draw a representative vector, and there's its ijk. 2i plus 3j minus 1k meters. How much work is done by this force? And so I go back and I say, well, my work, of course, is equal to the F dotted with D, or scalar product of the force vector and the displacement vector, which is the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. I got two choices here. I can either try to find the magnitude of D and the angle between these guys. Whoops, it is. This is not going to be very easy to draw. Or I can find the vector which is F. And so I decide it's 4 newtons pointing in a negative direction. That's going to be 0i minus 4j 0k. So one skill is, can you make a vector given a magnitude and a direction? And then the next thing is, can we do a so-called scalar product? Well, I say that work is equal to 0i minus 4j plus 0k scalared with or dotted with 2i plus 3j minus 1k. The way you do the scalar product is you multiply the coefficients by each other and add them all together. So 0 times 2 and minus 4 times 3 and 0 times minus 1. That's 0 added to minus 12 added to 0, which is minus 12. The negative in this indicates that you're taking energy out of the object. So if the object has a velocity, the velocity will decrease. The work is being done in such a way that you're taking energy away from the object. That's what the negative sign means. That if it was positive, the thing would be getting more energy and it would be, for example, speeding up. Be careful with dot products. I'm actually learning to call them scalar products again, because I'm amazed how often students will give me a vector answer to a scalar product, and I think it's because in their mind they're calling them dot products and cross products, which is what we do, but dot product doesn't reinforce it better be a scalar answer, whereas scalar product does. So a little alarm bell there, making sure that you've got that. This next question, how much work is done by this force during this journey? Well, the force, if you look at it, is changing as the displacement changes. And so it's this classic, well, you can get it. Newtons times meters is Newton meters, which is energy, joules. So this journey is the shape underneath. And so I need to find the area under that. I say work is equal to the integral of fx dx, which is the area under the trace. I recognize that this shape here is a trapezoid, as is that shape there. And so again, I like to write my own diagram, 0 and 4 and 3 and 9. So the work is equal to 1/2, because it's the average, 9 and 3, the average height, multiplied by the width, which is 4. And then for the second one, I'm going to average these two heights. That's 9 and 6, which makes whatever that is, times the width, which is there. So it's the average of the heights times the width. So this is 12, 2 times 12 is 24. This is 15, 2 times 15 is 30. Gives me 54 for the answer. Force acts on a 6 kilogram particle. The force varies with position. The force is defined by this equation, where F is in newtons and X is in meters. The force and the displacement are in the same direction. I don't have to worry about the angle between them. How much work is done by this force between 2 and 4 meters? So it's not the right graph, it's just a representative graph. And here's the bit I'm interested in. So I say work is equal to integral of fx dx, which equals the area under the trace. So the work is equal to, well, the integral of fx, which is 2x squared minus 4x plus 1 dx. Well, work is equal to, well, let's have a look. I increase my power by 1 and put it in the denominator. So that's 2 over 3 x squared minus 4 over 2 x squared plus x. And my limits are between 2 and 4. And then I'm substituting in. 4 4s are 16, 4 16s are 64 times 2 over 3. 4 4s are 16 times 4 over 2. Got to subtract that. 4. We're going to add that. And then we do a subtraction. And then for the 2, it's 2 2s are 4, 2 4s are 8, multiplied by 2 over 3, minus 2 2s are 4 times 4 over 2 plus 2. And you just carefully in your calculator work that out, and you get the answer of 15.3. Next one. 3 types of energy we deal with: spring potential, gravitational potential, and kinetic. This is a graphing question. A student plots a graph of spring potential energy versus spring extension. Which trace best represents the graph? The equation, you always need the equation. The spring potential energy is 1/2 times k times x squared. And I look at my graph, and spring potential energy is US, and spring extension is x. So, is it linear? Is it inverse? Is it inverse squared? Is it quadratic? And I think it's easy to see that's quadratic. So it would be E. But let's say you didn't spot it. Then you'd say, okay, let's this half k, let that equal 1. Just get rid of it. It's just 1. Put down values of spring extension. So 0, 1, 2, 3. It's 1 times 0 is 0 squared, and 1 times 1 squared is 1 squared, and 1 times 2 squared is 2 squared, and 1 times 3 squared is 3 squared. And then let's work that out. That's 0, 1, 4, 9. Do myself a plot. I can see it. Oops, a daisy. I can see it. So either recognize it from the form or do yourself a little plot to work it out. Almost there. A spring is located 6 meters above the baseline. Here's my baseline. The spring gives a block a speed of 12 meters per second. So here's my block. So here's my block. And here's my block. And this spring is pushing it. And it gives it a speed of 12 meters per second. So that 12 meters per second is after the spring has stopped pushing. The block travels on a frictionless track, falling into a valley. There's the valley. And then comes to rest on an incline. So it comes to rest here. How high is this point above the baseline? So I want that h. In first glance, it looks complicated, and I can make it really complicated in the middle just to mess with you, because you are comparing the start with the end, and what happens in the middle is, you know, not really important, because what we're recognizing is that when this track is frictionless, then the mechanical energy at the start, wherever I define the start to be, equals the mechanical energy at the end, wherever I define the end to be. So I look at the start, and remember, it's 12 meters per second after the block has reft the spring. It said the spring gives the block a speed of 12 meters per second. So it's got kinetic energy at that point, a half mv squared. It's also got height, so it's got potential energy, mgh. Now, forget about the valley. I'm comparing with the end, and at the end, it's comes to rest. So it's got no kinetic energy at the end. It's only got height energy. It's only got a gravitational potential energy. So I'm just putting numbers in. A half times the mass times the velocity squared plus a mass times the gravitational field strength times the height is equal to the mass times the gravitational field strength times the height. So notice the masses cancel. Notice I never told you the mass. This is teachers being devious. Again, we want you to write in full sentences. If you are of the habit of, well, I'll work out the initial kinetic energy, you'll go, it's a half times m times 12 squared. Ooh, I don't know m. I cannot work that out. Well, let's try the other end. It's going to be the height at the end. Oh, I don't know what m is. Oh, well, let's do the potential energy in the middle. Oh, I don't know what m is. And people will say, I can't do any of this because you did not give me the mass. And the teacher just smiles and says, well, do your best. Because the fact of the matter is, if you write an equation, the m's cancel. They're not significant. So we say, well, cancel out the m's, and we get 72 plus 60 is equal to 10h. 132 equals 10h. 13.2 equals h. So a very nice question, but notice be careful. If you're not writing in full sentence, in full equations, then you're liable to miss some issues because you're not going to see what cancels and what doesn't. Kind of squeeze this in. A 4 kilogram sled slides across a smooth and level surface with a constant speed of 8 meters per second. So there's my smooth and level surface. There's my block. There is a 0.6 coefficient of friction between the sled and friction-filled surface. There's the friction-filled surface. How far does the sled slide over the friction-filled surface before it's slowed to a speed of? And there's my final speed. Okay. Okay, so I know that there's friction involved here. And so my mechanical energy at the beginning plus my work done by friction, which is negative, equals my mechanical energy at the end. And because this is all on a level, my mechanical energy is made up of kinetic energy. So I can say my kinetic energy at this point at the beginning plus the work that I'm going to lose from friction is equal to what I have at the end. If you think about it, by the time I get to the end, there were 2 bits that happened. I had some mechanical energy and I lost some energy through work. So they want to go on the other side of the equal sign. And I say, well, a half mv squared plus, well, the work done by friction is minus ff times d, ff is in the negative direction, is equal to the kinetic energy at the end. It's not 0 in this case because I didn't have you wait until the thing stopped. So it's a half mv final squared. And so we plug it in and we say half times 4 times 8 squared from here. And then I say, oh, I don't know what ff is. So I say, well, ff is equal to mu k times fn. ff equals 0.6 times 40. ff is equal to 24. It's pointing in a negative direction, so it's minus 24 times d. And that equals a half times 4 times 3 squared, because that was the final velocity, was 3 squared. So 128 equals minus 24 times d, which equals 18. 24d equals 128 minus 18, which is 110. D is equal to 110 over 24, which is 4.58. Again, nice. It's a set piece. It's a classic situation. So expect to see a skier or a block or something on a friction surface or sometimes snow, but this is a classic problem. And then next, an 8 kilogram block is raised 9 meters vertically into the air by a motor. So here's my motor, here's my block, and here's my 9 meters. Let's have a look. It's going to be a weight of 80 newtons. It takes 2 minutes for the system. If the system is perfectly efficient, what is the power of the motor? I'm assuming here that this thing is moving at a constant speed. And so if it's 80 newtons weight, it's 80 newtons as a lifting force. It's a reasonable assumption. And then I say, well, power equals the energy change, or if you like, the work done in a given time. And in this case, the work is going to be the force times the displacement, lifting force times the displacement. And the lifting force, if you like, would be mg times d. You could recognize it as 80, but you could put it down as 8 times 10. And then you say, well, it's 8 times 10 times 9 over 120. 120, where did that come from? 2 minutes, yeah, but 2 minutes is not SI units. You've got to convert the 2 minutes into 120 seconds. Gives you 6 watts. Very nice problem. Sometimes people, it's interesting, sometimes they want to put minus 10 here for this G. And that's a mistake. That's because they've been dealing with G for free fall. And so they're calling it minus 10 as the acceleration due to gravity, but I prefer to think of it as the gravitational field strength. It's the mass times the gravitational field strength. It happens to cause a weight that points downwards. But in this case, I'm talking about my force which is doing the work, which is the lifting force. Cool. A pickup truck is rated at 450 horsepower. Express this in watts. Given that, you don't have to remember this, but given that there are 746 watts per horsepower, so 450 horsepower, well, we have horsepowers on top, so we want to put horsepowers on the bottom. That means watts has to go on top, which is 1 horsepower is 760 watts, which gives us that. And then, then we have an extra credit. I won't bother with the extra credits because well, I'll do them just because they're here, so why not? So to remind ourselves, we asked extra credit often from the test that was previous. So in this case, a diver jumps up off a high board with a velocity of 8 meters per second. So there's my initial velocity. The high board is 12 meters above the water. What is her velocity as she reaches the water? So I say, well, what links these things? Vf squared equals Vi squared plus 2a delta x. Vf squared is equal to, well, that's plus 8 squared plus 2 times a. My acceleration is minus 10 meters per second squared times delta x. And this is where people get caught out. The delta x is a vector, and it goes from the beginning, the start, to the end. And so it's not 12, it's minus 12. That's critical. So we have Vf squared equals 64 plus 240, which makes 304. So Vf equals the square root of 304, which is plus or minus 17.4 meters per second. And here's the second catch. This is going downwards, so you can't have the positive answer. It must be the negative answer. So that visualization, right at the very end, that visualization, are you doing math or are you doing physics? Because if you're doing math, you're just going to put down a whole bunch of numbers. But if you're doing physics, you'll look at your diagram, because you're drawing a diagram, and you'll say, well, that must be a negative value. And it's significant. If I asked you to drive to Miami, but you drove to Atlanta, and you said, I'm just as far away from Tampa as I would be if I went to Miami, so I got the right numerical value, I just got the wrong sign. You know, I'd say, what are you thinking about? You're like 1,000 miles away from where you should be. You know, this is craziness. It's a huge difference going to the wrong city. Well, that sign is a huge difference as well, so watch out for it. And then circle all the vectors in the following list. Well, velocity is a vector whether it's average or not. Speed is not. Distance traveled is not. Acceleration has a direction and a magnitude, so that's a vector. Mass just has magnitude. Time just has magnitude. So a nice straightforward question to end up the test. So there we have it. I hope this helps. It's giving you insights into my thinking of it. This is me trying to get the problems right. It's not me trying to teach this. This is my key. This is how I work the problems. You can see my handwriting is a bit rushed and it's not as neat as it could be. But I'm writing down every step, because I've learned the hard way that if I don't write down every step, I will make more mistakes and lose more points than I am prepared to lose. And that's the choice you're making. Okay? There we have it. Thank you. Did it not record?